So as I said, we are going to learn about Boolean laws in this specific video. We are going to start with idempotent laws. So I call the first three laws the 3I laws. Okay, I call the 3I laws. The first one is idempotent laws. Okay, idempotent laws, where we talk about only one signal. Okay, one specific signal or one specific variable. And next one is what I like to call the identity law. Okay, the next one is the identity law, where we incorporate with 0 and 1. And then finally, we have inverse law, where we have talk about the inverse of a given signal. Okay, so let's start with idempotent law. Okay, so we have idempotent law. So what is this? Yeah, what is this? Actually, when you are learning about laws, you can learn it in two ways. Okay, one, you can think of them as just some rules. Okay, and then memorize them, apply them to come up with the answer. Okay, apply them to come up with the answer. By answer, I mean simplifying a specific circuit. Okay, or expression. Second way is to understand actually what's happening. Okay, so in this video, what I'm trying is I'm going to do in the second way. Okay, I'm not going to give you just the law and then do some practice questions. No, that's not what I'm going to do. I'm going to explain how this actually works. Okay, how this actually works. If you think that you don't need that, you can skip. No worries. Okay, because if you know the laws, that's enough, right? Because you can apply and find the answers. But if you want to learn how this works, okay, the reason behind things, well, please stick to the video completely. So, first of all, idempotent law. The first law says that A dot A is equals to A. Okay, A dot A is equals to A. The second idempotent law says that A plus A is also equals to A. Okay, so these are the basic laws that are discussed in idempotent law. Okay, so how do this work? Well, you have to understand by using the gates. Okay, here we have dot, which means we are using an AND gate. Here you have an plus sign. Okay, so we are using an OR gate. So let's pass A. So this, let's say this is A. So let's have the signal line here. Okay, let's pass. Okay, let's pass A through an AND gate. Okay, let's pass A through an AND gate. Let's see what happens. Okay, so can we do that? Obviously we can. Okay, we can definitely do that. So obviously we can. So here we have A. Here also we have A, which means the output is A dot A. Okay. Now also you have a small doubt. Well, I know this is A dot A. How can you say this specific A dot A simplifies to A? What is the law? Okay. How that comes? Well, let's look at the truth table, shall we? So here we have A. Okay. And then let's say we have A dot A. Okay. So since we are running only one input, okay, since we are running only one input, we can just have two combinations, only 0 and 1. Okay. So tell me, since A is equals to 0, what will be A dot A? Well, that will be 0 dot 0, which means 0 and 0 is equals to 0. Okay, which means that is actually A. Why? The value of A in this specific case is 0. So when you do AND gate with two of those A, then you get the output as A. Similarly, 1 dot 1 will also give you 1, which means here also the output is A when A is equals to 1. Okay, so this is how actually idempotent law works. Okay, now let's see what happens when you send it through an OR gate. Okay, let's talk about that. So here we have the OR gate. Okay, so if you send A again and again through an OR gate, you'll get A plus A. Okay, so what is A plus A? So let's go to the truth table. Okay, so we have A and then A plus A. Okay, so A is 0 or A can be 1. If A is 0, A plus A is 0 plus 0, which is equals to 0, which means I can say the output is equals to A. Similarly, when A is equals to 1, 1 plus 1 is equals to 1. So the output will be equal to A. Okay, so the idempotent law states that A dot A is equals to A plus A is also equals to A. Okay, pretty straightforward, nothing too fancy. Okay, now let's talk about identity laws. Okay, now let's talk about identity laws. Okay, identity laws. Okay, identity laws are very straightforward. Okay, identity laws are very straightforward. So if you look at this, let's say we have A dot 0. Okay, so when you multiply anything by 0, okay, multiply in Boolean algebra, we don't say multiply, we say we are using AND gate, right? If you do an expression or if you perform AND calculation on two signals, and even if one of them is 0, we clearly know the output should be 0. Okay, similarly, if you multiply A by 1, what will you get? Or perform the AND function on A and 1, what will you get? You will get A. Yeah, you will get A. How are we going to explain this? Well, we will use the AND gate. Okay, so here we have the AND gate. Okay, so let's pass through A and 0 here. So output will be A dot 0. Okay, so if you look at the truth table, here we have A and then we have 0. You may think, since we have two inputs, shouldn't it be like 4 rows? Well, no, we don't have actually two inputs. Okay, because 0 is a constant. Okay, 0 is a constant. It's not going to change to 1. Okay, that's the idea here, right? So we don't need 4 rows. We just need 2 rows, which is completely dependent on A, variable A, or the signal A. So A can be given as 0 and 1. 0 is always 0. There is no change. Okay, so what will be 0 dot 0? It will be 0. Okay, and 1 dot 0 is also equals to 0. So whatever the value of A, okay, whatever the value of A, output is always 0. So this is equals to 0. Similarly, we can also do for 1 also. So let's have an AND gate. Okay, let's have an AND gate, and let's pass through A and 1 through the AND gate. So you'll get A dot 1. Okay, so here we have A, here we have 1. A dot 1 is here. Okay, so A can be 0 or A can be 1. 1 can always be 1. Okay, so A dot 1 will be 0 dot 1. 0 dot 1 is equals to 0, and 1 dot 1 is equals to 1. Okay, so if you have 1, okay, if you have 1 as one of the AND inputs, the other input decides whether you get the output as 0 or 1, and it is actually that signal that we are using. So 0, which means this one represents A, okay, and this one represents A. Why? The only thing that is changing here is A, and according to A, this guy is changing. Okay, so this is the first set of identity laws where we use AND gate. Now let's use OR gate. So the next one is A plus 1 is equals to 1. Okay, so if you revise the gates, okay, in OR gate, we learned that if any one input is 1, okay, any one of the inputs is 1, the output should be 1. Okay, that's what we learned in OR gate. Okay, I hope you remember. I will add the description. I will add the link to the description. Okay, so A plus 1 is equals to 1. Okay, A plus 1 is equals to 1. That we know. What about A plus 0? What will it be? Well, A plus 0 is equals to A. Okay, so you can also understand by using, the OR gates. Okay, so here we have OR gate. First of all, let's pass through A and 1 here. The output will be A plus 1. Well, A dot 1 is equals to A. So what should we do here? Well, we have A, we have 1. The output is A plus 1. A can be 0 or 1. 1 can always be 1. Okay, so A plus 1, 0 plus 1. What will 0 plus 1 be equals to? Well, 0 plus 1 is equals to 1. Okay, and 1 plus 1 is equals to 1. So whatever the input is, okay, it doesn't matter if you have one signal that is equals to 1 in the OR gate. Okay, so if you have a plus sign and a 1 there, well, you can you can simplify the circuit into just 1. Okay, so the answer will be 1 and 1, which means it is equals to 1. Okay, similarly, let's do for 0 and A. Okay, let's do for 0 and A. So here we have A, here we have 0. The output will be A plus 0. Okay, so we have A, we have 0, the output A plus 0. So A is 0 and 1, 0 is 0 and 0. So what will 0 plus 0 be equals to? 0. And then 1 plus 0 is equals to 1. Why? 1 plus 0 is 1. That's what OR gate is all about. Okay, so according to A, the output changes. If A is 0, output is 0. If A is 1, output is 1. Therefore, A plus 0 is equals to A. This is what we call the identity laws. Okay, the 4 identity laws. Okay, that's it. Now let's talk about inverse laws. Okay, in inverse law, we are going to talk about the inverse of given functions, inverse, complement, the bar, etc., whatever you want to call it. Okay, so first of all, we have A dot A bar. Okay, A dot A bar is equals to 0, and then we have A plus A bar is equals to always 1. Okay, these are the two laws that we normally use. Okay, this is very important. Keep in mind, this will come in handy in multiple places because we are going to use this to actually explain some of the other laws. Okay, so how can we do this? Well, let's do the same thing. Let's have the signal. So let's draw the diagram. So we have A. Okay, first of all we need A passing through AND gate. Okay, and then we need what? A bar, which means we are going to pass it through a not gate before we pass it through other gates. Okay, so we have A and A bar coming through, and they are passed through an AND gate. Okay, so we have A here, we have A bar here, so the output will be A dot A bar. Okay, so now what do we need? Well, we have A here, okay, and then we have A bar. Since it's a single signal, even though A bar is a fancy name, but it's still a single signal. It's just a derivation of A. So we don't need multiple rows. We just need two rows. And we have A dot A bar. Shall we try? So if A is equals to 0, A bar should be 1. If A is equals to 1, A bar should be 0. Remember the NOT gate, okay? The inverse or one's complement, whatever that you want to call, it's fine. So A dot A bar, 0 into 1 will be equals to 0, and 1 into 0 will be equals to 0. So look at here, whatever the input A is, okay, it can be 0, it can be 1. Does it matter? No, it doesn't, because the output is always 0. So that is equal to 0. Okay, similarly, we can do for A plus A bar also. Okay, we can do for A plus A bar also. So let me draw that properly. So here we have the OR gate, and we are passing A through a NOT gate first, and it is passed through OR gate with A. So here we have A, this is A, and this is A bar, and the output is A plus A bar. Okay, so let's start. We have A bar, and then A plus A bar. Yeah. So if A is 0, A bar is 1. If A is 1, A bar is 0. 0 plus 1 is equals to 1. Remember the OR gate, even if one of them is a 1 in OR gate, well then the output will be 1. Okay, similarly 1 plus 0 is also equals to 1. Doesn't matter what the input A is, the output is always 1. So the output is always 1. That is what we call the inverse law. Okay, so why are we learning these laws? Well, we are learning these laws to actually, we are going to simplify logical circuits. That's why we need them. Okay, we are learning them to simplify the logic circuits. Okay, I know if I am giving you questions in this, it's not going to be that much hard, but let me give you some questions like this. So let's say we have A dot A, okay, A dot A plus, okay, A dot A plus A dot A bar. Okay, if you have something like this and they ask you to draw a logic circuit, it's a little bit hard actually. Okay, it's a little bit hard because we need OR gate here, we need AND gate here, we need AND gate here, we need a NOT gate here. Nearly 4 gates are required, minimum 4 gates. Okay, minimum 4 gates, we need minimum 4 gates. But if you can simplify this expression, you won't need 4 gates, trust me. Okay, so this is the main important way of solving a Boolean expression. Okay, so what can we do is, so here we have A dot A. Okay, A dot A. We know A dot A is equals to A. Okay, that is the idempotent law. Okay, and then we have plus A dot A bar. What is A dot A bar? Think of it. Inverse law. A dot A bar is equals to 0. Okay, so here we have A plus 0. Okay, we have A plus 0. We know A plus 0 is equals to A. That's what identity law suggests. Now tell me, do you even need a single gate? Okay, do you even need a single gate? No, you can just pass through A instead of drawing all these things. Okay, if you had to do according to this expression, you'll have A coming through inside an AND gate. Okay, and then you will pass A through an OR gate along with a NOT gate. So it will be like this, and then you will pass it through an AND gate, and finally these two will go through an OR gate. Okay, and finally you will get all this expression. Let's say this is equals to Z. Okay, so you'll get Z here. Okay, tell me, do you have to do this, or can you just pass it through wire? That's enough, and the output will be enough. This is why we need to simplify. This is the need of simplifying Boolean expressions. Okay, and this will come in handy when we are doing, scenario related practice questions. Okay, scenario related questions. For example, let's say you have to, there are two conditions that should be met when you have to do something, when an output should be given. For example, if the light is on, okay, if the light is on, and the fan is on, okay, well, you can say the current is too much. Okay, if the light is off and the fan is on, you don't have to say anything. If the fan is off and the light is on, you don't have to say anything. If both are off, you don't have to say anything. So there you have to use an AND gate. That's just an example scenario. Okay, that's just an example scenario. That's not required here. But I'm telling you, when it comes to simplifying, we need Boolean laws. Okay, so let's do another question. Okay, let's say we have something like f is equals to, okay, a plus a dot 1. Okay, a dot 1. What will be the output? First of all, we have to simplify this. What is a dot 1? A dot 1 is equals to a. That's what identity law suggests. And then a plus a is equals to a. Why? That is idempotent law. Idempotent law suggests. Okay, so that's it. Now let's do something like this. Okay, let's say we have q is equals to a dot a bar, a dot a bar plus, okay, plus a plus a bar, a plus a bar. What will we do? Well, a dot a bar is equals to 0. Okay, why is it 0? Well, it's 0 because inverse law suggests that. Okay, and a plus a bar is equals to 1. Yeah, a plus a bar is equals to 1. That is what we call the inverse law, the second inverse law. So 0 plus 1 will be equals to 1. So whatever the input a, it doesn't matter, the output will always be equals to 1. Okay, that's the idea behind this. Okay, and I want to give you one small question. Okay, something like, let's say we have b, well, we'll say a is equals to x plus ab, well, not abc, well, bcd plus FGH, okay, plus QXYZ, okay, plus X bar. What do you think will be the output? Okay, what do you think will be the output? Well, if you see it like this, well, it's very hard, you don't know anything about B, we don't know about anything about C or D. There are too many inputs here, okay, but what your eye should see is there is an X, and there is a plus X bar. Okay, so X plus X bar is equals to 1. Okay, so you can reduce this into 1 plus BCD plus FGH plus QXYZ. Okay, so whatever the inputs B, C, D, F, G, H, Q, X, Y, Z, it doesn't matter. There are 10 inputs there, 6 plus 4, 10 inputs. Okay, whatever the 10 inputs are, doesn't matter. The output will always be equals to 1 because that's what identity law states. Okay, 1 plus anything, 1 plus any signal, 1 plus 0, 1 plus anything, you can short circuit this. That's the meaning of this. Okay, you can short circuit this. So 1 plus anything is equal to 1. Okay, so these 4 questions are enough in this one. I don't want to, make this a big deal. Okay, these 3 laws are like basic laws. It just comes in practice. Okay, just trust me, it will come in practice. But just spend some time, as I already always say. Okay, so we'll talk about the next 3 laws. The next 3 laws are car laws. I call them the car laws. Okay, they're not very important, but at the same time, you will use them. Okay, you will use them. Yeah, in the next video, we'll talk about the car laws and then also the triple D laws. Okay, we have finished the triple I laws. We have to finish triple D laws and the car laws. Okay, so stay tuned. Thanks for watching the 7th video in our Logic 8 series. If you found this deep dive into the 3 I Boolean laws idempotent identity and inverse helpful. Don't forget to like, share, and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos. Check out the full playlist to master logic gates. Follow us on Instagram, and I will see you in the next video. Until then, keep learning and stay curious. Bye bye.